Well, now we know that image texture is one of the most fundamental visual descriptors, and there are different applications in which it can be usable. For example, texture-based image segmentation, texture synthesis, texture analysis/classification, content-based image retrieval, shape from texture, etc. Now, there are four different um, basically strategies which are used for texture feature extraction, or generally we can say that all the methods can be divided into four different strategies. Number one is statistical methods. They deal with the statistical properties of the spatial distribution of gray level values. um, then there are the model based methods, in which the construction of models is done that can actually describe the textures. Then we have the structural based methods, in which we take the definition of textons or texels that we have already talked about. The basic primitives are textons or textiles, and their repetition is basically described as per the structure that is defined. And then the signal processing based methods, they are based the methods which are based on spatial and frequency filtering, and wavelets, etc. One important thing is that since we are trying to incorporate the properties of a region into a number of values. Therefore, the aspect of statistical estimation or a statistical description of the content in the image will always be there. So even when you're using, for example, signal processing based methods, it means that we are pre-processing the images using several, filtering based methods, and then after that we will have to calculate some statistics so that all the properties of the regions can be compressed into a couple of coefficients that will effectively describe the texture content in the images. So, although in the literature these categories have been separately described, but they can be overlapping somehow, because the aspect of statistical bias is always there in any kind of method. The textons and the models and the structural based methods, they are also used, but the most commonly used methods are statistical and filtering based methods. And on the backdrop of this, we specifically talk about these two, about some texture based descriptors which correspond to the statistical and filtering based method. So the very first texture descriptor, or we can say, in 1973, Heralick was the name of a researcher who proposed the GLCM based texture descriptor. GLCM stands for gray level co-occurrence matrices. And in this method, we basically first of all calculate a co-occurrence matrix. We'll show you how to calculate that in the next slide, or maybe the second one, and then we calculate the statistics of the co-occurrence matrices. Now how do we calculate the co-occurrence of a matrix? For example, on the left hand side, if we have an image patch, then we know that first of all we figure out what is the minimum gray level value which is there. In this case, it is 1. What is the maximum gray level value? It is 8. So we create a matrix of size 8 by 8, starting from 1 to 8, and then we try to see how do the gray level values appear in pairs. For example, the 1 1 pair, it appears only once. The 1 2 pair appears twice. Then the 1 5 pair appears once in the images, and so on. This is how we calculate all the statistics about the co-occurrence of two different gray level values. An important thing is that in this case we have the horizontal gray level co-occurrence matrix, in which we are just considering the neighboring right pixel, or the neighboring next pixel when forming the pairs. But it is also possible to calculate the GLCM, which is vertical. For example, this 1 2 pair will be included in a specific gray level co-occurrence matrix that will be for the vertical, or even diagonal values can also be incorporated. So it depends upon different researchers. How they form the gray level matrices and how they combine them, or if they do combine them at all or not, or they keep them separate. Well, once we have the gray level matrices formed, then we need to calculate some features from them. So there can be different features. I have just listed down a couple of them over here. But if we have a look at it in detail, there are about 22 different statistical measures of these co-occurrence matrices that tell us about the existence of the or the co-occurrence of the gray level values within the images. So these are what they are used, and their formulas are also listed over here. These are different layers of texture. For example, we have the contrast, we have the correlation, then we have the maximum probability, we have the entropy, we have homogeneity, and all these things are calculated as per these formulas. Well, in practice, this is how different GLCMs look like for different textures. For this texture, this is the GLCM. It's a random image with just salt and pepper noise. We know that, and so this means that we can have the polarized variations within the image consecutively. So this means that we can have a very random distribution of the gray level values taking place in the images, and thus giving us this very random GLCM. Then we have this case in which we have a sinusoidal wave, a basically vertical sinusoidal wave that is going on in the image, and this is how we know that a sinusoidal wave is would be smooth because the variations that are taking place in the image, they are going to be smooth. There is going to be always a gray level region that is lying between the high and the low. So that's why we will never be having the extreme values, which would be a combination of the two different poles, which means a zero gray level value and 255 or 255 and zero. We'll never be having these values there in these images. But we know that this is quite a regular image, so we'll be having a regular gray level covariance matrix, and we can easily figure out that the statistical properties of these two matrices will be very different as compared to each other. Then this is a more realistic image. And this is how the gray level co-occurrence matrix for this case looks like, and this is this is how a typical gray level co-occurrence matrix would look like. And over here we can see that since in case of the images we have an assumption that the neighboring pixels are highly correlated, therefore we'll be having always the GLCMs which have the diagonal values which are quite bright, and then we'll be having no or low occurrence of the gray level values in the polarized form, which means a significant jump from one gray level to the other. That will be very less in case of a more realistic image. And then once we talk about the statistical properties of the GLCMs for these three different cases, we obviously know that they will be different as compared to each other, and therefore, once we aim for recognition related tasks, we can differentiate between these three different cases. For example, using the statistical properties of the GLCMs in this case, and now we'll move towards a new descriptor that is called as the edge histogram based descriptor. These are called as the local descriptors in the images. They are widely used in the MPEG 7 standard, and in this descriptor, um, what we do is that we try to capture the spatial distribution of 5 different types of edges that can be there in the images. Well, we have the horizontal edge, we have the vertical edge, we have the oblique or 45-degree edge, we have the reverse oblique 135-degree edge, or the non-directional edges, which are going to be the random edges. And effectively, in order to calculate these types of edges or these kind of variations in the images, there are different filters which are already defined within the MPEG 7 standard, and these are the filters, the 3 by 3 masks which are usually used when we are trying to calculate these different features from the images.